Reboot the computer. CSC. No. Brown. Elliott. Gray. Hello, can you hear me?
Yes.
Yes.
Okay, how are you guys doing today?
Pretty good.
So,
Mr. Joseph,
yes,
Professor
ma'am.
Joseph.
Yes, ma'am.
So, you gave me a 0 on my classwork, and
Is it classwork or
it was the
Excel
classwork.
assignment?
Yes, it was the last classwork. And I worked hard on that.
I've not graded the last classwork. Are you talking about Excel assignment?
Yeah, the Excel assignment.
Yeah, okay. Yeah,
So
I must have written something for that reason for that, right?
Yeah, you did, but as I sent it, I wrote on there that I was having trouble with my Excel. I did it on Excel, but Excel wouldn't let me send it, so I screenshotted it and sent it that way. But you said you couldn't.
Well, this
go on there to look at it.
assignment is a Excel assignment, so I can't accept any other thing other than the Excel file. I would recommend that you do it in Excel because it's
Okay.
Excel assignment. So
Okay, well, I already resubmitted it. I figured out how to send it through Excel, so I resubmitted it already.
all right, because I graded this assignment today. Because of that, I'm going to grade it again, but not today. It's now a past due, a past due assignment now. So I'm gonna grade it when it is convenient for me. No penalty, but I will grade it. Yeah, you have to be patient.
Okay, thank you.
You're welcome.
Professor, did you say you didn't grade classwork 5 yet?
No, I haven't.
Professor.
All right. If you have any other question, let's deal with it after when the class is over. Okay.
Okay.
All right. Now tonight we'll be working on the theory of probability. You can see my screen, I believe. All of you can see my screen, right?
Yes, sir, Professor.
Yeah, okay, you can see. Okay, good. All right. Probability simply means the likelihood of an event occurring, Now, the principle of probability can be applied in various fields, in education, in health, medicine, sports, business. But actually the group that used it at first were gamblers. So after a while, it was discovered that it can be applied in different fields of human endeavor. So because of this, many examples we'll be doing in this topic. We have to do with gambling. Then of course we can apply it in other areas: business, education, health, sports, and so on and so forth. But understand that when we say probability of an event, we are referring to the likelihood of that event occurring. Now, an event with a probability of 1 can be considered a certainty. For example, in a coin, the probability of when you toss a coin, the probability of a coin that it will land head or tail is 1. It must land either head or tail. But if an event is impossible, it will have a probability of 0. For example, getting if you say that the coin will land, let me put it this way. The probability of getting an 8-day week is not possible because we have a 7-day week. But so that's impossible. But remember, in some places, the week days are different. Like in my place, my tribe, we have 4 weekdays, 4 days in a week. Even though after the British brought Western education, we now changed to 7-day week. But traditionally, in my tribe, it's 4-day week. Anyway, but now just worldwide, with a week is taken as 7 days, Monday to Sunday. So the probability of getting an 8-day week is not possible, and that would be 0. Okay. So we use 1 for the one that is an event that is possible, but for event that is not possible, we use 0. Now, how do we write probability? We write it in different form, 4 different ways. As a fraction, for example, you have 7 out of 10. As a ratio, 7 to 10%, 70%, for example, and decimal 0.7. Most of the examples will be using decimal or fraction, you know. Let's look at some of the basic concepts in probability. We start with the first concept, which is the probability experiment. A probability experiment refers to those chance process that leads to well-defined results. Those results, we call them outcomes. Any chance process that lead to some outcomes, well-defined outcomes, we call it a probability experiment. For example, when you flip a coin, we already know the outcome. Either it lands head or it lands tail. When you roll a dice have 6 sides. A dice, you can see a dice right here, normally has 6 sides. So one side, if you roll a dice, 1 might show up, or then 4 might show up, and so on and so forth. Another example of a probability experiment is buying a lottery ticket. Either you win or you lose. So that outcome is win or lose, and it is a chance process. Now, drawing a card from a deck, we have a card that a deck has 52 cards. Drawing a card from a deck is also a good example of a probability experiment. Now, checking the paternity of a baby, who is the father, can also be considered a probability experiment, because either he's the father or he's not the father, you know. Now, now you can, that I have shown you these examples. Now let's look at outcome, the next concept. Outcome simply means this result of a single trial of a probability experiment. For example, when a coin is tossed, the outcome is head or tail. So, so if you toss a coin, 1 minute. When you toss a coin, the outcome will be head, can be head or tail, or a tail, a tail. You know, so I can just put it together. I'll just put them together. This is the outcome. See, head or tail. Now, when you buy a lottery ticket, either you win or you lose. You win, come up, or you lose. When you take an exam, either you pass or you fail. That is the outcome. So now let's look at the sample space, the next concept, sample space. A sample space simply means the set of all the possible outcomes of a probability experiment. The set of all the possible outcomes of a probability experiment, called a sample space. For example, when you roll a dice, all the possible outcomes are 1 might show up, 2 might show up, 3, 4, 5, and 6 for a 6-sided dice. And how about the days of the week? all the possible outcome includes Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. See, that's the outcomes. So that will give you all the possible outcome when you pick, you want to select a day of the week. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Okay. Now, we can also find all the possible outcome using what we call a tree diagram. A tree diagram simply means a visual display of the outcomes of a probability experiment using branches, that originate from a starting point. Now, let's see how this works. We have look at this question. It says, find the sample space for the gender of the 3 children of a couple. Use the diagram. So let's find what the gender, all the possible outcome for this. Using a tree diagram. So a family decided to have 3 kids. What are the possible outcomes for their gender, the gender of their kids? So for that, I'm going to use a tree diagram. So let's say that B is for boy and G is for girl. Now the first child, of course, then I'm gonna use B for boy. Of course, I'm gonna use B for boy. Okay. And then I'm gonna use G for girl. So that the first, make sure that I'm seeing this again. So the first child is going to be either boy or a girl. So for the second child, all the possible outcomes, you're gonna get boy and girl for this part and boy and girl for this part. Okay. So we have it's gonna have boy and girl for this one. And for this one, we also have boy. And then all the way down here, got girl. That's too far. Girl. So for each of these results, this one will have a boy and a girl. This will have a boy and a girl. So you have boy. Okay. And
Professor,
I can't hear you very well. Can you say?
Professor, I don't understand.
We are
Can
trying
you hear
to
me?
find. We are trying to. Hey, I can hear you now.
I don't understand. Yeah, what is happening with the connection between the first and second child? Why are there twice as many options for the second child?
Well, what we are trying to get all the possible outcomes. So, for the first child, you have boy and girl possibility, right?
Okay.
Yeah. Then for the second child, all the you have to get. We're looking for all the possibilities, which means for each one you gonna have a boy and girl, and for this one you're gonna have a boy and girl. So
I see, because you're trying to figure out
all the
how many different arrangements of children you could have.
Yeah,
Okay.
all the possibilities. Okay. Yeah.
Okay.
So
Yes.
to do that, you have to
Thank you.
assign boy and girl for each of them.
Okay. Thanks.
Then assign boy and girl for this. Then for the third child, you do the same thing. Assign boy and girl for each of them. Okay, for the third child. So I got boy, girl, boy. Okay. Yeah. Girl. boy, girl. And for each of them, remember, for each of you are trying to get all the possibilities. So for each of these, probably assign boy and girl for each of them. And girl. So I mean, for the third child, all the possibility we have, maybe boy, girl, boy, girl, boy, girl, boy, girl. So you can see that now let us get all the outcomes. Now this is first child, boy and girl. For the second child, since you're trying to get all the possible outcomes, you're gonna assign boy, girl for each of them. We did it, and we repeated it here. So now let's get the outcomes. The outcome might be that the first child is a boy, the second child is a boy, and the third child is a boy. That gives us PBB. Okay. It might be that the first child is a boy, the second child is a boy, and the third child is a girl. Because BBG, it might be that the first child is a boy, second child is a girl, third child is a boy. BGB, or that the first child is a boy, second child is a girl, third child is a girl. BGG. So we keep going that way. These are all the possibilities. So you have GBG. I mean, the first child might be a girl, second child a boy, third child a boy. So you have GBB. Maybe the first child is a girl, second child is a boy, third child is a girl. You have GBG. See? So you keep going that way. Oh, I'm gonna put this in. Okay. Sometimes computer act weird, but you're gonna fix this. Okay. Then I'm gonna move it back. It might be that the first child is a girl, second child is a girl, third child is a boy. So that we have girl, boy. Or that the first child is a girl, second child is a girl, third child is a girl. So we have 3 girls. Okay, girl. So these are all the possible outcomes, and they become what we call the sample space for this. If you see any family that have 3 kids, their gender must fall in any of this group. 3 boys, 2 boys and a girl, 2 boys and a girl, 1 boy and 2 girls. It must fall in any of this group. Any family that have 3 kids. Oh, okay, I think so you call it sample space. So all the outcome, all the possibilities, we call it the sample space for this. If you have any question, please ask me right now on this. So that
So
our sample
there are 8 possible outcomes.
Exactly, 8 possible outcomes. See, 8 possible outcomes. Now, because there are how many? Why 8? Because there are 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. And if you're asked to find something, suppose you're asked to find the probability that the family has 2 girls and a boy. Suppose that you're asked to find this. Find the probability that the family has 2 girls and a boy. Now, the outcomes for 2 girls and a boy are as follows. So you have 2 girls and a boy here, GGB, GGB, comma, and you have GBG, comma. Just 2 girls. That is 2 girls and a boy. You have BGG, BGG. See, these are the outcomes that give us 2 girls and a boy. These are the outcomes that give us 2 girls and a boy. So that since you're asked to find the probability that the family has 2 girls and a boy, so you can have P here represent probability. 2 girls and a boy. How many of them? 1, 2, 3. That's going to give us 3 out of 8 possibilities. 3 out of 8 possibilities, which is when you put it on a calculator, 3 out of 8 will become where is my calculator? Okay, 3 out of 8. 3 divided by 8 give us 0.375, 0.375, 0.375, or you can call it, you can call it 37.5% chance. See? So when solving probability, get the sample space first, then get the outcome that you need and divide them, you get your answer. And if you're asked to find the probability that the family have only 3 girls, say 3 girls, 3 girls. What is this outcome for 3 girls? Only one, GGG, right? Okay, GGG. So 1 outcome. So that the probability that the family have 3 girls is 1/8, which is from the from our calculator, 1/8. You change this to 1. I got 0.125. 0.125. 0.125. Or if you like, I can call it 12.5%. So there's 12.1% chance that the family will have only 3 girls. See? So that'll give you an idea. Any question on this before we go to the next section? Any question?
Can I see the way that the question is written out up top?
You mean the first one, this one here?
No, the first one. All the way up there.
You mean this one?
Yes.
Okay.
Okay. Thank you, Professor.
You're welcome. All right, let's see. Next one is the event. An event is a set of outcomes. And we have 2 types, the simple event and the compound event. Now, a simple event is an event with 1 outcome. For example, when you roll a dice, if you roll a dice and getting a 6, the outcome is only 6, is 1 outcome. You roll a dice and getting a 2, the outcome again is 1, just 2. So we call it a simple event because it has 1 outcome. So now a compound event. A compound event had more than 1 outcome. That is, it have 2 or more outcomes. For example, we roll a dice and get an even number. Even number in a dice is 2, 4, and 6. See, it has more than 1 outcome. We call it a compound event. Another one, getting a weekend is so if you are selecting the days of the week, and getting a weekend is getting Saturday and Sunday. See, more than 1 outcome. So we call it a compound event. So at this point, we're ready to look at some more information about the probability of an event. So we have if an event have a probability of 0, it is considered to be impossible. I have already mentioned that. So that we have the probability of an impossible event is 0. Now, for unlikely event, the probability of an unlikely event is less than 0.5. 0.5 means 50%. For example,
we have to have a more than 50% chance of getting COVID. I bet most people in this class have gotten COVID.
No. I'm talking about after the vaccine. You,
No, vaccine, I had it. How many people in this class got COVID? I want to know.
I don't know. I don't have that information.
Everybody, I'm pretty sure.
Are you sure?
After the vaccine,
No,
right?
no, don't say that. I don't.
Yes, after the vaccine.
After the vaccine, I'm telling you,
Sir, be
we
quiet.
all had COVID.
Okay.
I never got vaccinated and only had it once.
So that means it is no longer unlikely, right?
It's not unlikely.
Okay. Now, so I'm gonna change it to the probability of getting let me see what I will use to change it.
Like the measles, say the measles.
Measles?
Definitely not likely that anyone here is going to get the measles.
But you know, measles. Okay, let's use measles. Measles. Okay, let's change to measles. That's a good idea. So it's less than 50%, right?
Definitely less than 50%.
Good. Now, likely event, that means that event will occur is more likely. So when it is more than 50%, is likely to occur. For example, when you toss a coin, it can land the head or tail. That one is likely. So now that's likely. Now we can look at the approaches to probability. The way or you can also call it the types of probability. We have the classical approach, empirical or relative frequency approach, or the subjective method. Now this one, the subjective, is because it is subjective. We don't really use it much because it doesn't. It's not reliable. So now you have somebody's. Give me 1 minute. Let me see. Let me reply to she person having problem logging in. Okay. I don't normally do this when I'm teaching, but she's trying to log in. So let me see. Tali. Okay, so her name is Talia. Okay. Reboot. Give me 1 minute. Reboot your computer. And try again. Try again. Okay. So I can continue. Because he was sending me from the remind. Anyway, let's start with classical. Classical probability. In this approach, we compute the probability of an event using the known sample spaces. Okay. For example, we know that the dice has 6 sides already. We know that the day of the week have 7 days. And we know that the eggs have a dozen of egg has a dozen contain 12. It's 12. Now we know that a card has 52 cards. A deck has 52 cards. So we call it classical. More examples, say the sample space of a dice is 6 because the dice has 6 sides. A coin, 2 sides. So we know the sample space already. So now we use them to calculate the probability of the event. And under classical probability, we use the formula PE. We have this P represent the probability of event is number of ways E occurs or number of outcomes of E divided by the sample space. For empirical probability, we don't we don't know the sample space, so we have to estimate the sample space by ourselves. That's the only difference. Now, the subjective, I've already told you that with that one, politicians use subjective probability a lot. That's why some people, when they make estimate and put percentages, some people believe them, some people don't believe them. So they make a lot of because it is subjective. For example, the director of a state welfare agency might estimate that there is 70% chance that a proposed revision in eligibility rules will be passed by the state. That is just his opinion. So we don't use subjective probability in our calculations. We use only the classical probability and the empirical probability. So let's start with the sample space. It says, the first question says, find the sample space for rolling 2 dice. Find the sample space for rolling 2 dice. Okay. Now we have the first dice has 6 sides, 1 to 6. The second dice have 1 to. So if you throw the 2 dice, that means it might be that we might have 1 showing up on the first dice and 1 showing up on the second dice. That gives us 1, 1. Or it might be 1 showing on the first dice and then 2 on the second dice, giving us 1, 2. Or it can be 1 shown on the first dice and 3 on the second dice, giving us 1, 3. So we follow that pattern, we get 1, 4, 1, 5, 1, 6. Now it can be that the 2 showed on the first dice and then 1 on the second dice with 2, 1. Or 2 showing on the first dice and 2 on the second dice, 2, 2. Or 2 showing on the first dice and 3 on the second dice, 2, 3. And then you follow that pattern, you get 2, 4, 2, 5, 2, 6. Follow all the way to the last number. We gotta get this. And this is the sample space. And when you count them, you have all the possibilities here. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So the sample space here is 36 possible outcomes. 36 possible outcomes. See? So we answered our question. The question is want us to find the sample space for 2 dice. If it is 1 dice, it's only 6 possible outcomes. But since there are 2 dice, 36 possible outcomes. Any question on this? Okay, good. Now the next question says, find the sample space for drawing a card from an ordinary deck. Now you can see the card we have here. And you can see that it has 4 suits. Miss Lee have finally, she made it in. So I'm gonna bring her in. There are 4 suits: club, diamond, heart, and spade. And each of them have how many? Let me see how many cards in under the club suit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So club have 13 cards, and each of them have 13 cards. Diamond also has 13 cards on the suit. Hearts also have 13 cards. Then spades also have 13 cards. So the sample space, now if you add all of them, 3 plus 3 is 6, plus 3 is 9, plus 3 is 12. I'm going to write 2 here. Now, carry 1, put 1 here, become 1 plus 1, 2, 3, 4, 5. 52 cards. So that the sample space is 52 cards. Okay? Yeah, that's how you find it. So I have shown you 3 ways you can find a sample space. Now let's look at examples on classical probability. It says a card is drawn from an ordinary deck of 2 cards. So it says find these probabilities of getting a jack, of getting a 6 of clubs, of getting a 6 or a 3. Let's start with the first one. The probability of getting a jack, okay, will be, now let's go to the cards. How many jacks do we have? This is the jack right here. How many of them? 1, 2, 3, 4. So that the probability of getting a jack is 4 out of 52 cards. here, 4 out of 52, which will give us 4 divided by 52, 0.077 rounded, 0.077. Or if you like, I can call it 7.7% chance of getting a jack. Okay. Part B says to find the probability of getting a 6 of clubs. Now, probability of a 6 of clubs. Let's see how many 6 of clubs we have. If you look at here, these are the clubs. Only one of them is 6. So that the probability of getting a 6 of clubs is 1 out of 52 cards. So we go to our calculator, have 1 over 52, it was 0.019, 0.019. Okay, or you have 1.9% chance of getting a 6 of clubs. You can see how slim your chances are. Okay. All right, and the part C says of getting a 6 or a 3. The probability of getting a 6 or a 3, which is equal to the probability of getting a 6 plus the probability of getting a 3. Okay, which will be equal to, for 6, how many numbers have 6 there? Say 6, 1, 2, 3, 4. So 6 cards have number 6 on them. So for 6, we have 4 over 52. And for 3, how many cards have the number 3 on them? 1, 2, 3, 4 of them. 4 over 6. 4 over 50, 4 over 52. And this will give us 8 over 52. And from the calculator, we're gonna get this as 8 divided by 52. 8 over 52. Give us 0.154. 0.154. 0.154. Or you can call it, if you like, 15.4% chance. 0.4% chance. Any question on this? Yeah. No question. Okay, good. Good. Excellent. Now let's go to the next question. It says, two dice are rolled. Find the probability of getting the sum of 7, the sum of 9, the same number on both dice, the sum of 11. Now, first thing is to find the sample space. We have it, we did it before, so I just put it here. And it has 36 possibilities, I mean to say, 36. So with that, we can answer the questions. The first question says, part A says, the sum of 7. Now, outcomes give us sum of 7 include the following. We can see 6 plus 1 is 7. 5 plus 2 is 7. 4 plus 3 is 7. 3 plus 4 is 7. 2 plus 5 is 7. 1. So these are the sum of 7. 6, 1. I'll have 5, 2, 5, 2. These are the outcome that give us sum of 7. Have 3, 4, 4, 3, and 3, 4. Have 4, 3, 3, 4, 4, 3, 3, 4, then 2, 5, and 1, 6. 2, 5, and 1, 6. Okay. These are outcomes that give us sum of 7. And how many of them? 1, 2, 3, 4, 5, 6. So that the probability of the sum of 7, the probability of the sum of 7 equals 6 out of 36. 6 by 36. So we can go to the calculator and get the answer. 6 divided by 36. 6 divided by 36. 0.167. 0.167. 0.167. So that the probability of getting a sum of 7 is 0.167. Now, part B says the sum of 9. So to get that, what outcome give us sum of 9? Sum of 9. The outcomes that bring us to that should be, look at this. 6 and 3. So somebody's coming in. Let me bring her in. Okay. So you have someone. It's a sum of 9. You can see 6, 3, 5, 4. This 5 plus 4 is 9. 4 plus 5 is 9. 3 plus 6. So we got 6, 3. We got 5, 4, and 4, 5. 5, 4, 4, 5. We have 3, 6. So that the probability of getting a sum of 9, okay, equals how many of them? 1, 2, 3, 4. How many? So 6, 2, 5, 3. I forgot. Okay, sorry, 6, 3, 5, 4, 4, 5, 3, 6. Okay, this is going to give us 9. So there are 4 of them. 4 divided by 36. So from our calculator, we can get it as 4 by 36. 4 divided by 36. 0.111. That's the answer. 0.111. 0.111. So that the probability of getting a sum of 9 is 0.111. Now, the same number on both dice. So, okay, somebody's coming in again. Thomas. I'm out. I got it today. Okay. Now, so how many? Let's find the outcome that give us the same number. At C. Same number. Same number. Okay. On both dice. Maybe. Now, I see 1, 1, 2, 2, 3, 3, 4, 4, 5. These are the same numbers. So you got 1, 1. Okay, 2, 2. 3, 3. 4, 4. You got 5, 5. Got 6, 6. So how many of them? 1, 2, 3, 4, 5, 6. Okay. That's 6 of them. So that means that the probability of getting the same number equals 6 over 36. And 6 over 36, we calculated 6 over 36 right here. See, just 1.167. Okay. So the probability of getting the same number on both dice is 0.167. Then the last one there is of getting the sum of 11. For the sum of 11, that's part D. Okay. Sum of 11. What outcomes give us a sum of 11? Well, we have here, if you look at the chart, you can see 6 plus 5 is 11, and 5 plus 6 is also 11. So we have 6, 5, comma, and then 5, 6. Okay. So that the probability of getting, okay, sum of 11 will be equal to 2 divided by 36. So 2 divided by 36, we can get from the calculator 2 divided by 36. 0.056. 0.056. So that is it. Any question on this one?
I'm sorry, guys, because I wasn't here for it. Do I just have to watch the video, or is it a quick thing you can do over again?
Well,
Just
I want to know what the
I missed the whole thing.
Oh, that in that case, I would suggest you you continue from where you started.
Okay,
Then after you watch the video, because we cannot go back from the beginning. We are gone.
that's fine.
Yeah, we have gone a long way.
All right.
Yeah. Now let's look at another example. It's a roulette has 38 slots, numbered 0, 0, 0, 1, 2, all the way to 36. Now it says half, and you can see from this roulette here. See, you can see the 0 here and the 0, 0. And you can then the numbers 1 to 36, the rest of them. Now it says here, half of 1 through 36 are red, and the other half are colored black. The remaining number 0 and 0, 0 are colored green. So find the probability that a ball lands on a black number, a green number, a 10, and an odd number. So now from 0, you have 0, so that there are 38 slots there, or 38 number, because it says 0, 0, 0, then 1 through 36. So a total of 38 slots or 38 numbers. So we'll use B for black, G for green, and reds for R. Now, this is a classical probability. Why? Because we know the sample space to be 38 slots. So now, how many black we have? Black B equals, it's a 1 through 36. Half of it is black. That means 18 are black. 36 divided by 2 is 18. 18. Then red is also 18 because the other half is 18. Then the rest of them, which is 2 of them, the green numbers, G, is only 2 of them, making it the total of how many what's the total of how many slots we have? A total of 18 plus 2. So let me just make sure. So you got 18 plus 18 plus 2 is 38 slots. 38 of them. Total of 38. So we have our sample space. Now we can answer the question. It says, find the probability that a ball lands on a black number. That's A. So that the probability of a black number, which is B, equals how many black numbers we have? 18 of them. So you have 18 over 38. So you have 18 divided by 38, which we can get from the calculator. 18 divided by 38 is 0.474 rounded. 0.474. 0.474. Or you can see that it has how many chance? 47.4% chance of landing on a black number. Now, next one is if the ball land on a green number. Okay. So for B, how many green numbers do we have? We're looking for the probability of green numbers. At the ball land on a green slot of green number is, we have only 2 of them, 2. So that the required probability becomes 2 over 38. So 2 divided by 38, we can get that from the calculator. So change this to 2. 0.053. 0.053. Or there are 5.3% chance that it land on the green number. Now, usually, if the casino we not, I think when you bet on it on the slot, you pick a particular number, it will land. I think that's how they do it. I don't know. I haven't played roulette before, but when I say that slot land on a number 10, so the at part C, the probability that it lands on a number 10 equals how many 10s do we have? There's only one number that is 10 here. Let me show you here. It is where, so you can see the 10 right here. Only one number is 10 here. Only one number. So that the probability that it lands on 10 is 1 out of 38. Okay. So again, you go to the calculator. 1 out of 38. Okay, 1. 0.026. 0.026. Or I can call it, excuse me, 2.6% chance that it lands on the number 10. Matter of fact, in any of those numbers, 2.6% chance. But D says it lands on an odd number. Well, it says a half of 1 through 36 are red, and the other half are black. So half is half an odd number, half an even number. So it's 18. So that the probability that it lands on the odd number, a slot with an odd number, is 18 over 38. So which will give us we have let me see, 18 over 38. We get this one 18. 0.474 rounded. 0.474 rounded. 0.474. And look at you cannot bet that it land on a black number in a casino because they will be losing money. They're a very big probability. Or 0.47 or 47.4% chance. Now, any question on this one? Okay, excellent, excellent. So now we can proceed to the next example. So now, by now, I've shown you examples of that involve classical probability. I've shown you the dice, the card, the dice, and I now just showed you about the with the roulette. Now, at this point, we're going to review some other basic rules of probability. Now, I'm going to take you to where those rules are located. So those rules are as follows. First one is rule number 1. It says the probability of an event E is a number, either a fraction or a decimal or a percent. It's a number between and including 0 and 1. And this is how we write it. 0 less than or equal to PE. This PE means the probability of event E less than or equal to 1. And what does this mean? It means that the probability of an event can never be negative, can never be a negative value, and can never be greater than 1. Now, rule number 2 says, if an event cannot occur, then its probability is 0. Yes. The probability of getting a 3-sided coin is not possible. So it's an impossible event. And
I'm sorry, can you just show the formula for the first one again?
Right here, it's right here. You mean this one here?
Yeah, thank you.
You're welcome. So now, for 3 says, if an event is certain to occur, then the probability of the event is 1. For example, getting an even number, getting let's say a head or a tail when a coin is tossed. Or I wouldn't say that because they both have 50-50 chance. Now, getting let me put it, a 7-week day, any day, getting a Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, getting a day of the week when you make a selection. Getting any day of the week is possible, is a possible event. You can pick any, that means any day can be picked. Okay. Now, there's one we call complementary rules. So I'm going to take you back to where we were before. Rules of complementary rules. Okay, that's the other rules we need to learn. Complements are the simplest way to explain it is that it is the opposite. For example, the complement of you being here is you not being here. So if sitting down, if it's an event, and standing up is another event, then the complement of sitting down is standing up. So it is the opposite. But the way we define it in this under the probability theory that the complement of an event E is the set of outcomes in the sample space that are not included in the outcome of the event E. So this is how we write it here. E with a small c, or you can use any letter that you are in. If it's you are looking for the probability of getting an ace, then you're gonna use A, the small c. So that means complement of A. Now, for example, let's see this example here. It says find the complement of each event. The first one says, I'm gonna bring this down. So the first one says selecting a letter of the alphabet and getting a vowel. The complement will be not getting a vowel. So the complement will be getting this. Getting a B, C, D, F, G, H, J, K, L, M, N, P, Q, R, S, T, V, W, X, Y, and Z. See? So the complement is getting not getting a vowel. How about this second one? It says selecting a month and getting a month that begins with a J. The complement is getting month that does not begin with J. That means getting, okay, February, March, April, May, August. Okay. Oh, I didn't spell it out. August. September. October. November. November. December. Okay. So that's a complement. And we can solve questions in probability involving complements. And this is the formula for it. The probability of E complement is 1 minus the probability of E. Now, let's try this example here. It says, in a lottery game, each player chooses a 3-digit number. Each player chooses a 3-digit number. And it says here, so the 3-digit number between 000 and 999. That means there's 1,000 digits. It says a player wins if his or her 3-digit number is chosen. Find the probability that a player buying a single ticket loses the game. So the win is the event. To lose is a complement. So in this case, they say find the probability that the player loses. So in this case, you're looking for the complement. To solve this, let us use W for win. Okay. So now, remember, it's choosing each player choose a 3-digit number from between 000 and 999. Now we have that means 000, 001, 002, 003, all the way to 999. So the 1,000 numbers. Now we have to win. Now we have to win. Win is 1 out of 1,000. Okay. So 1 out of 1,000 will be equal to 1 divided by 1,000. 0.001. 0.001. But the question was asking us to find the probability that the player loses. So the lose is W. So the probability of that they lose for complement, probability that they lose, which is WC, equal, okay, equal to 1 minus the probability that they win, W. Okay, which is equals to 1 minus the probability that they win, which is 0.001, what we got. That means they go to 1 minus 0.001, 0.999. 0.999, 0.999, or 99.9% chance of the player losing. So you can see why most people don't win lottery. Only a very tiny group that win this lottery. Because the chance is very slim. Any question on this one? Have a question? All right, since there's no question, we can proceed to empirical probability. Remember, I explained that under the empirical probability, in that case, you don't know what the sample space is, so you have to estimate it by yourself. Now, the formula we use for that is the probability of the event E equals to the frequency of event E divided by the total frequency. Let's try this application. It says, hospital records indicate that the maternity patient stayed in hospital for a number of days shown below. See, those that stayed, how many of them stayed 3 days? 15 stayed 3 days. 4 people stayed 32 days, and so on. It says, find these probabilities. First, a patient stayed exactly 5 days. B, a patient stayed less than 6 days. C, a patient stayed at most 4 days. D, a patient stayed at least 5 days. So again, the first thing to do is to find the sample space by adding all these numbers. So I'm going to write them down so I can add them. Let me write them down.
I'm sorry, Professor. Can you just show the formula again?
Oh, right here.
Thank you.
Welcome. So let me write them down so I can add them. 56, 19, 5. So let's go and add them. Okay. This is showing me, okay. We got so we got 15 plus Sarah, somebody's coming in. Sarah. Okay. Plus I got 32 plus 56 plus 19 plus 5. 127. That's what we got. 127. So I'll go here and put 127. That's our sample space right there. 127. Now with this, we can answer the question. The first question says, it says, maybe I should move this down. Let me move this down so we can have enough room. Okay. Now, the first question says, find this that the patient stayed exactly 5 days. Exactly 5 days. P. Okay. I want to make this should be 16. So you have exactly 5 days. Is the probability of 5 days. 5 days. Okay. 5 days. How many patients stay 5? This is 5 days. It's 56 of them stayed 5 days. 56 out of 127. So you have 56 divided by 127. And that will give us an answer. 56. 56 divided by 127. .441 rounded. 0.441 rounded. So that the required probability that the patient stayed 5 days is 0.441. And then part 2 say that a patient stayed less than 6 days. B, less than 6 days. B, How many pages? I mean, okay, let me make this in 18 because this one is too small. Okay. So that they say less than 6 days. So less than 6 days. So the required probability will be, this is 6 days. See, 3 days, 4 days, and 5 days are less than 6 days. So we're looking for this, how many of them? We're going to add this, and that. Because you can't count 6 days because it says less than 6 days. You will count 3 days, 4 days, and 5 days. So you're going to be the probability of 3 days plus the P of 4 days plus the probability of 5 days. Now you can pick this from the from the table. For 3 days, how many stays 3 days? Is 15 over 127. 15 divided by 127 plus, for 4 days, we have 32 over 127. 32 over 127. And for 5 days, we have 56 over 127. And that will give us the answer we are looking for. So I'm going to write this down. I'm going to write 15 over 127 plus 32 over 127 plus 56 over 127. Okay. So I have have 15 divided by 127. Okay. Plus 32 divided by 127. Yeah, plus 56 divided by 127. 0.811 is the correct answer. 0.811. 0.811. So that the probability that the patient stayed less than 6 days is 0.811. Okay. Now, next one will be part C. We say that the patient stayed at most 4 days. At most 4 days. Okay. So let's see that. The patient stayed at most 4 days. That means 4 days means 4 days or less. 4 days or less. So part C, the probability that the patient stayed at most 4 days. I'm going to make this 18. And not bold. Patient stayed at most 4 days. 4 days will be, look at the table, you're going to be 4 days or less. That means 3 days and 4 days. So you're going to be the probability of 3 days plus the P of 4 days. And for 3 days, we have how many stayed 3 days? 15 out of 127. 15 out of 127 plus the other one is for 4 days. So many stay 4 days. 32 over 127 and 32 divided by 127. And that will give us the answer. 15. Let me write this. Okay. Yep. Let me go and get it from there. The calculator. We have it already on the calculator. I just have to remove one of them. 0.370. Rounded. 0.370 is the probability that the patient stayed at most 4 days. Okay. But this says to find the probability that the patient stayed at least 5 days. At least 5 days means 5 days or more. You can see from here 5 days or more. That means it's gonna be 5, 6, and 7. So that the probability that the patient stayed 5 days, at least 5 days. 5 days will be equal to the P of 5 days. Yeah. Okay, let me check this person in. Plus the probability of 6 days plus the probability of 7 days. I can see them from here. 5, 6, 7. For 5, I have 56 over 127. So for 5 days, equal 56 over 127. Plus for 6 days, I have 19 over 127. 19 divided by 127.
Professor, I gotta go.
Okay. Now, for the 7 days, we have 5 over 127. 5 over 127. 5 divided by 127. So let us work this out. Okay, we have to write this down. We got 56 over 127 plus 19 over 127 plus 5 over 127. Let us work this. So you got 56 divided by 127. Okay, plus 19 over 127. Okay, plus 5 divided by 127. 0.6299. So I'm gonna write this. If you round it properly, it's gonna be 0.630. 0.630. 0.630. Okay. And then so that we can now we answered all the questions. Now, any question on this? If you have a question, ask me.
This kind of like last week, Professor. I got questions, but I don't know how to ask them. I'm gonna have to look at that video again.
You mean the last one? This last one?
Yeah.
You have a question on this one? This last one?
I don't know how to ask it, so I'll just have to go back and look at the YouTube video.
Okay, okay.
Hello, I'm sorry. I don't want to interrupt the class. I'm sorry. I wanted to say excuse. I wanted to apologize because I totally forgot today was Friday, and I came in a little late. Like I came at because it slipped my mind like today was Friday. I thought today was Thursday, so I want to apologize.
Oh, no problem, no problem. But do you have any questions for now?
And well, I don't even know what's going on. I'm just gonna watch the video because I came late, so I don't know what
Okay,
But yeah.
I'll make the video available. Just continue from where you started with us. Okay.
Yeah.
So that if you have a question as we proceed, let me know. Okay. All right. Let's continue. So now let's look at this. Yeah, it's more concepts. Mutual exclusiveness. Two events, A and B, are said to be mutually exclusive if they cannot occur at the same time. For example, if standing up is an event and sitting down is another event, That means you cannot sit down and stand up at the same time. Am I right? So they are mutually exclusive. How about this event? Getting a 4 and getting a 6 on a single card. It's not possible, right? Either you get a 4 or you get a 6. So it's mutually exclusive. And in an intersection, either you turn a right or you turn a left. You can't turn left and right at the same time, right? So we also say that they are mutually exclusive. Now, how about you can be a Democrat and a Republican at the same time, can you? Is it possible to be a Democrat and a Republican at the same time? Hello, guys?
You can be
No.
moderate. You can be a moderate, but that's kind of a third category.
Yeah, but moderate, you're not a Democrat, you're not a Republican. So
No.
this one is you can say a moderate Republican or a moderate Democrat, but you cannot be a Democrat and a Republican at the same time. Can
Okay.
you? Yeah.
No.
So next thing is dependent event. Two events are dependent if the occurrence of one event affects the occurrence of the other event in such a way that their probability will change. For example, the event getting good grades and the event getting a scholarship, they are dependent. If you get the good grades, then you get a scholarship. See, it increases your chance of getting the scholarship or the probability of getting the scholarship. Now, how about this? Drawing a card from a deck, not replacing it, and then drawing a second card. So you can see that when you draw a card from a deck, before you make the draw, there are 52 cards. You make the draw. Now there are 51 cards. So you can see that when you want to calculate the probability of the second card, it will change. So when you park in a no parking zone, the event parking in a no parking zone and the event getting a parking ticket, they are dependent. Yeah. Now, so they say that they are dependent events. Now, for independent events, two events A and B are independent if the outcome of event A does not in any way affect the outcome of event B. For example, if you win the Maryland lottery, that does not mean that you're gonna win the New York lottery. They are totally independent. And we have different rules for all this. We have addition rule. The addition rule says the probability of event A or B equals to the probability of event A or B equals to the probability of event A plus the probability of event B minus probability of event A and B. Now, if they are mutually exclusive events, this part will change to 0. Now, there are multiplication rules for independent events. Now, how do you know you are going to use addition rule? If the keyword there is or, see, when they say or, the question say or, A or B, that tells you that you're going to use addition rule. But when they say and, that means you'll be using the multiplication rule. And the multiplication rule say for independent events say that the probability of event A and B equals to the probability of event A times the probability of event B. And if there are 3 events, they mean that they are looking for the probability of event A and B and C. That means that it is equal to the probability of event A times the probability of event B times the probability of event C, and so on and so forth. But for the dependent event, they change a little bit. For example, you said if the 2 events are dependent, then the P of A and B equals to the P of A times P of B given A. This forward slash means given that. So for dependent event, it means that the probability of event A and B equals to the probability of event A times that is the probability that event A will occur times the P that event B will occur, given that event A have already occurred. And so on and so forth. Now let's try some examples that involve these rules. Yeah, let's try some examples that involve all these rules. Because when I list them as rules, they look confusing, but when you apply them, you see that they are actually friendly. He said, at a political rally, there are 20 Republicans, 13 Democrats, and 6 independents. If a person is selected at random, find the probability that the person, that he or she is either a Democrat or an independent. So let's use R for Republicans, D for Democrat, and I for independent. The key word there is all. See? That tells you that you're going to use this formula here. Okay? Because you say all. Either a Democrat or an independent. So that's, let's say Republicans, we have Republicans equals 20 of them. Democrat equals 13 Democrats. And the independent equals 6. So that the total that we have there will be total. Okay. I gotta write this down and add them. 20 plus 13 plus 6. I got
39.
say it again. Huh?
39.
Yeah, 39. Okay, 39. Correct. 39. 39. So you have 39 here. Total is 39. All right. So now with this we can answer the question. The probability of getting a Democrat or an independent will be equal to the probability of getting a Democrat plus the probability of getting an independent minus, excuse me, the probability of getting a Democrat and an independent. Which is equal to, for Democrats, how many Democrats we have? 13 of them. Is 13 out of 39.
How are you going to get a Democrat and an independent?
Your voice is breaking up, Miss Elder. Can you say it again?
How do you get a Democrat and an independent?
Well, that's what the formula says. The formula says the formula for the for addition rule says here A or B equals the product of A plus the P of B minus P of A and B. Now, if they are mutually exclusive, this side will change to 0, right?
Okay, so this should be 0.
Yeah, so yes, we are coming to, yeah, exactly. So we have, for the independent, you have 6 over 39 minus, then Democrat and independent, that's not possible. So you gotta be 0 over 39. Okay? So that will give us 19. Oh, let's just go and put it on the calculator, right? The way it is. So you have 13 over 39 plus 6 over 39 minus 0 over 39. Let's go and put it in our calculator. We have 13 divided by 39, okay, plus 6 over 39, okay, minus 0 over 39. That gives us 0.487, 0.487. So that the probability of getting a Democrat or an independent is 0.487. Any question on this? Okay, excellent. Now let's try another example. It says here, a card is drawn from a deck and then replaced. Then a second card is drawn. So before you draw the card, anyway, let's just continue. Find the probability of getting a queen and then an ace. See, this is and is the keyword here. And then an ace. Say a card is drawn from a deck and then replaced. Then a second card is drawn. Find the probability of getting a queen and then an ace. Let's use Q for queen and A for ace. Now I say and tell us that we are going to use using the multiplication rule. So the probability of getting a queen, and an ace will be equal to the probability of queen, okay, times the probability of an ace. Now, before you made the selection, there are how many queens? 1, 2, 3, 4 queens. So you got 4 out of the 2 cards times. Now, it says it was replaced, so we still have 52 cards. Ace, how many aces do we have? 1, 2, 3, 4. So also 4 over 52. And that will give us the required probability. 4 over 52 times 4 over 52. I can just make it 2, 4 divided by 52, okay, times 4 divided by 52. 0.0059, okay, 0.0059. So that the required probability is 0.0059. Any question on this one as well? Any query? Okay. Excellent. Very good. Now let's try this one then. Since there's no question. It says a person owns a collection of 30 CDs, of which 5 are country music. If 2 CDs are selected at random, find the probability that both are country music. So this case, they didn't tell us that it was replaced. So we assume that it was not replaced after the first selection. Let us use C to represent country music. Now, we are looking for the probability that the first CD, C1, is a country music, and the second CD, C2, is also a country music. Now, because they are not, he did not replace it after he made the first selection. That means they are dependent events, since it will no longer be 30 CDs. So anyway, let me put this way. It gotta be the probability of C1, okay, times the probability of C2, given that C1 have already occurred, okay, because they are dependent events. So since it was a selection without replacement. Now, let's see what the result will be. Now, before he made the first selection, there are 5 country music in, because he said if 2 CDs are selected at random, so he made 2 selections. So before they made the first selection, there are 5 country music out of the 30 CDs. So you're gonna be 5 over 30, right? Times Now, he did not replace it. So before he made the second selection, there are now only 4 country music and 29 CDs. So you have 4 over 29. And that will give us the answer. So 5 over 30. 5 divided by 30. Okay. Times 4 divided by 29. 0.023. 0.023. 0.023 is the answer. Any question on this? Good, good. No question. Good. Excellent. So let's look at this. Now it says here, a Harris poll found that 46% of Americans say they suffer great stress at least once a week. Now, if 3 people are selected at random, find the probability that all 3 will say that they suffer great stress at least once a week. Now, let us use S to represent great stress. So here it said 3 people are selected at random, and we are required to find the probability that all 3 will say they suffer great stress at least once a week. So that means we are looking for the probability that the first person, S1, suffers great stress, and the second person, S2, suffers great stress, and the third person, S3, suffers great stress. This would be probability of S1, okay, times the probability of S2 times the probability of S3. See? That will give us the answer we are looking for. So it's a multiplication rule. Okay. All right. Now, there's one thing we need to know before we can apply this formula. He said that 46% of Americans, so they say that they suffer great stress. So they already given you the probability, but they want you to find the probability that of these 3 people, that all of them see that they suffer great stress. So because you see here that a Harris poll found that 46% of Americans say they suffer great stress. So for the stress, it says is equal to 46%. 46%. Which is, when you change it to decimal, it's gonna be 0.46. Okay. Now you can plug it in here. We are looking for the probability that the S1 and S2 and S3, that means the probability of S1 times the probability of S2 times the probability for S3. So for S, we have 2.46 because they say that it's 46% of Americans. So it's gonna be, so the answer, to get the answer, you're gonna do this 0.46 times 0.46, since there are 3 of them, 0.46. And that will give you an answer. So I got 0.46 times 0.46 times 0.46. Okay, 0.097. 0.097. 0.97. Any question?
Yes,
Go ahead.
Professor.
Yep.
How do 3 numbers times each other equal a smaller number?
Miss Elliott, this has nothing to do with me. It is what the calculator gave us when we multiply that.
How? How is that possible?
Okay, you didn't see when I multiplied it?
What? How
You
is this possible?
Watch me then. Watch me again. 0.46 times 0.46 times 0.46. See, it had nothing to do with me.
Yes, but can you explain why that's true?
The only way you can explain it, I can see with be that, see, when you're multiplying with decimals, right? Like this, number that involve decimal. How many? This one have 2 decimal places, right? This have 2 decimal places. These have 2 decimal places. So whatever answer you get, you're gonna move it 6 decimal places to the right. Okay, let me do it this way. Do you understand that this one have 2 decimal places, right? You understand that, right?
Yes, but yes, but
hold on,
okay.
I'll explain. Hold on. Then after you can ask me. Just hold on, eh? This one have
Okay.
2 decimal places, right?
Uh-huh.
And these are 2 decimal places. So you have 6 decimal places, right?
Okay.
Now, watch me now. Let me multiply them as if there's no decimal, right? 46 times 46 times 46. See?
Yes.
Now you're gonna move 6 decimal places to the right. So let me write this number down, and then I'll explain to you more. Give me 1 minute.
This isn't making it make more sense because that only has 5 digits, but you had 6.
Hold on, I'm coming. Let me write it down. 99736, right? So now remember we have 4 decimal. So let me go take you to this place and write it down. We got 97. Okay, 336. Now look at this. How many decimal places? 1, 2, 3, 4, 5. So if starting from the back, you count 1, 2, 3, 4, 5. The 6th number, there's nothing there, so you gotta make it 0 before you put your decimal point. See?
Okay.
So you count from it. So you multiply the count the number of decimal places. You move numbers 6 places to the right. Now, when you move the first 5 numbers, because you have only 5 numbers, right? You move the first 5 numbers, 1, 2, 3, 4, 5. There's nothing here anymore, but you're supposed to move 6 numbers. So so that space, you replace that space with 0 before you put your decimal point. And of course, 0.0, right?
Okay.
That'll give you 0.097. Yeah.
Okay. So basically when you're dealing with numbers less than 1, things get weird.
Yeah, less than 1, it gets weird a lot.
Okay.
I mean, that's the best word to use for it.
Thank you.
You're welcome. Now, any other question before we go to the next example? Okay, now, okay, good. Now look at this. It says, the result of 985 pedestrian deaths that were caused by accidents are presented below. You can see the table. Pedestrian intoxicated, driver intoxicated. You can see yes and no for pedestrian, and yes and no for drivers. He said, if one pedestrian death is randomly selected, find the probability that the pedestrian was intoxicated or the driver was intoxicated. Part B says, if 2 pedestrian deaths are randomly selected with replacement, what is the probability that in both cases, both the driver and the pedestrian were intoxicated? So find the probability that in both cases, both the driver and the pedestrian was intoxicated. Now, to answer this kind of question, the first thing to do is to find their sample space. That means you're going to find the column totals and find the row totals first. So let us find the column totals first. This one is 59 plus 79. So I'm going to have 59 plus 79. 59 plus 79 give me 138 for that one. So I got 138 here. Then this one is 266. That'll be 266 plus 581. So that means 260 plus 581. So I'm gonna go and get it from here. We got 266 plus 581. Give me 847. 847 here. Then to get this part, 59 plus 266. I'm gonna have 59 plus 266. So I'm gonna have okay, 59 plus 266. Give me 325. 325. 325. 325. Then I'm gonna add this one. 79 plus 581. So you have 79 plus 581. 71. Oh, sorry, 79 plus 581. Give me 660. 660. 660. Now add this to get the final, which is this will be the sample space here. I'm gonna get 325. 325 plus 660. So you have 325 plus 660 is 985. 985. 985. So and if you add this one, you will also get 985. So now that's the first part. And this part you're gonna be careful because if your answer here is wrong, then every answer you get will be wrong. So be careful when adding the numbers. Now we're ready to answer the question. Let us use P for pedestrian was intoxicated. PC for driver was intoxicated. So for pedestrian was not intoxicated. D for driver intoxicated, and DC for driver was not intoxicated. Now we have to find, if one pedestrian death is randomly selected, find the probability that the pedestrian was intoxicated or the driver was intoxicated. So this is the keyword here, or. That tells you that you're going to use addition rule. So that the probability that the pedestrian was intoxicated or the driver was intoxicated now becomes the P of P. That means the probability that the pedestrian was intoxicated plus the probability that the driver was intoxicated minus the probability that the pedestrian and the driver are intoxicated. So let's put the numbers. Okay. This first one will be for the pedestrian see the pedestrian right here. And this is yes. This here show the place that they're intoxicated. And the total is 325 out of 985. 325 out of 985. Plus, for the driver, you can see the years for the driver right here. And the total is 138 over 985. 138 divided by 985 minus where both the pedestrian and the driver were intoxicated is right here. You can see this place. You can see yes here and yes here. You can see that they intersected here. This number showed where both the pedestrian and the driver are intoxicated, which is 59 over 985. So that will give us the answer we are looking for that section. So we have equals, let me write this down and put it in a calculator. We have 325 over 985 plus 138 over 985 minus 59 over 985. Let's go and put this on the calculator to get our answer. Okay. So you have 325 divided by 985. Okay. Plus 138 divided by 985. Minus 59 divided by 985. 0.410 rounded. 0.410. Or you can call it, if you like, 41.0% chance that the pedestrian is intoxicated and the driver was intoxicated. Our answer becomes 0.410 or 41.0% chance. Now, for part B says, if two pedestrian deaths are randomly selected with replacement, what is the probability that in both cases, both the driver and the pedestrian was not intoxicated? See, this is and, which means that you're going to use the multiplication rule. And, see? So both the driver and the pedestrian was not intoxicated. So that part B says the probability that both the driver and the pedestrian was not intoxicated. If you look at here, this is the no for pedestrian, that they are not intoxicated. And this is the no for driver, they are not intoxicated. So where both of them are not intoxicated is right here. See? Right here. Both the driver and the pedestrian were not intoxicated. And there are two people selected. That means the probability that the driver, DC, was not intoxicated, DC, and the pedestrian, PC, was not intoxicated, PC. Okay. PC, this C means complement. Okay, remember the complement. PC, control. Okay. And for the driver, not intoxicated, will be equal to the probability of the driver not intoxicated. Okay. Plus and times. Let me put this C. Okay. Times the probability of the pedestrian not intoxicated. I mean the PC. Okay. Not intoxicated. So like I said, this is the section that tells us that we have the both of them see no for driver, for pedestrian, and then no for driver. This is the intersection where both of them are not intoxicated. So you can call it, can be equal to 581 over 985 times 581 over 985. 581 over 985 times 581 over 985. especially because it said that they were replaced with replacement. So that means the answer will now become 581 over 985. Excuse me. We go and then 58. Let me write this down. Let me write it down first. 581 over 985 twice. So I'm gonna go here and put equals 581 over 985. Okay, times 581 over 985. 0.348. So we got 0.348. So let's go and put it 0.348. Which is 0.348. Or if you like, you can call it 34.8% chance that both the driver and the pedestrian was not intoxicated. Now remember, because this is you're multiplying the same thing twice. You can even do it this way. You can say you can just do 581 divided by 985. Okay. Raised to the power 2. It will give you the same result, 0.348, which is the same thing that we have here, 0.348. Now, any question on this one? Any question? Okay, excellent. So that in our next class, we'll be working on what is called conditional probability on Monday. Working on conditional probability starting from Monday. So now, before I want to show you for this week, what you have this week, the announcement. I hope you guys read my announcement because it contains important information. First of all, you're in chapter 4, and this is the homework for the week. I'm going to put the class work as soon as the class ends. I'm going to put the class work. So complete homework 4, then complete the Excel assignment 2, and then classwork 6. So these are the assignments due this week. Now, any question before we leave?
What is the Excel assignment going to be on?
Well, it's there already. Let me show you then. Let me show you from this. If you go to the models, and then this is week 6, I believe. We are still in this model. Yeah, that's where we are. Model. So Excel assignment is right here. Is on the measure of central tendency. If you open it right here, so you are required to use the I made a video here how you can do it.
Okay.
Yeah, so you just watch the video and then follow the steps there.
Okay.
Now, any other question before we leave?
Yeah.
Okay, I'll let someone else go and come back.
All right.
Okay, so when I was taking the I don't know if everybody else had the same issue as me, but when I was doing the homework on, I think it was Alex, it was some I guess some of the questions were on topics that we haven't even gone over yet.
That's why. Oh, that's. I mean, for what homework is that? Is that for?
The last one that was due Sunday.
This coming Sunday?
No, that was due last Sunday. The previous week.
Yeah. That's we finished everything last Friday. Everything last Friday, and that's homework. Those questions I picked them up by myself. So I chose everything we did. I made sure that I didn't ask questions outside what we did. And that homework
on Alex, it was.
But in that homework was I made it available when was and it was there for like three weeks. That's why I made it available for 3, so that by the time you finish it, I will have covered everything. And I made it multiple attempts. So I put it there. It stayed there for 3 weeks. So when you're doing it, if we haven't finished it before Friday, of course you will see. If you did it before Friday, of course you're gonna see things we haven't covered. That's, like I said, that's why I made it available for 3 weeks. But on Friday we covered everything. That it was due the Sunday of that week. So, any other question?
I have a question about the grading.
Huh?
I have a question about the grading on one of the Alex assignments. I can't recall if it was the test or the homework.
You mean the classwork or homework?
I can't remember which one, but one of the answers, the option was none, and when I wrote none, it didn't accept my none. I'm not sure if it was written wrong or if I had extra space or something, but I'm not sure if you could go back and check that. And I don't know if anyone else had that same issue.
There's a button.
I think I know what you're talking about.
Huh?
That I think it was like question. I want to say it was question number 1 on the Alex thing, but it's more than one of the answers. So it was more than like it was like a negative something, and then it was like 145%. It was like I had to pick like 3 different answers for mine.
Yeah, because I think it's the first question that says determine whether this is correct for probability, right?
Yeah.
No, I'm not talking about that.
Not
I'm
that
talking
one.
about
I'm sorry.
maybe
It's like a little box.
It showed me the answer afterward. But what I'm referring to is the correct answer was none, and I was marked wrong even though I had written none.
So how do you know that?
There's a little box. There's
how
a
do you
little
know-
box next to it that says none, and you have to click the box that says none. You can't actually type in none. Does that make sense?
It will tell you to
Oh my
choose the
goodness.
correct answer.
Yeah, that makes sense. It is stupid, but okay. Jeez.
All right, any other question?
Yes, is the
Can you
homework due
go
tonight
over-
or tomorrow?
You mean the classwork?
Yes, the classwork, is it due tonight or tomorrow?
Well, the classwork is due the same day we have a class, but I still accept it the next if you submit it tomorrow.
Okay,
Some of them you still got us marked late for too, though.
Huh?
Some of the other classworks that you said we had time, like we had for the next day, are still marked late. I don't know if anybody else.
Well, I didn't
take off.
I didn't take off points from it because of I don't normally because I know the when you submit the classwork, it will tell me, it will show me when you submitted it. So
okay,
if you see
so
my
if it says late, it's okay if it's saying late, because I got 2 assignments that say late.
it will say late, but tomorrow. But I will not accept. I will not take it as late because it was me that said submit today or tomorrow. So I have. If you look at my comments on my grading for the classwork, I haven't said that. I haven't mentioned that you submitted this late because
All right, thank you.
You're welcome. Any other question?
Yes. Can you please go over the histogram that you said I did wrong, because I just want to see what I did wrong.
Which are the histogram?
Like for the Excel assignment 1, you said the histogram was formatted wrong, so I just want to see what I did wrong.
Let me see if I can pull it out from here.
Oh, because I think that there were spaces between the bars. I did like a bar chart.
Spaces. That's mentioned.
Yeah. Okay.
Because histogram bar chart has spaces. Histogram doesn't have spaces.
Okay. Thank you.
And you're going to be posting this class, correct?
Do you mean the video?
Yes.
Sure, I will. I'll post it there. Any other question?
Yes, I have a question. I remember I told you about my Alex. I was not able to log in for the first, I guess the first homework assignment.
Homework 1?
Yes, I was wondering, did you figure out how I was going to be able to make that up? And
what will happen if I am just like you guys, I'm still learning how to use that Alex to, if I reset assignment So what I'm
Yes.
gonna do is, like I said, last week of April, I'll be looking at my grade book and attendance. That time, remind me, I may have to give you a hard copy to do work and submit to me. Okay?
That's fine. Another thing.
But you have to maintain your attendance in good standing. Make it at least 80% attendance score. That will qualify you.
That's another thing is too, like I was just like one of my class peers just stated, it is things in Alex that we're doing that we're not taught in class. So are we supposed to go off of a book? Like, how do you want us to do it? Because I understood what she was saying. A lot of things that's in Alex that we're doing for home assignments, I'm not seeing you review. I done been in your class, almost every class. I'm not seeing you reviewing all of the material. Some of the material, yes, we are reviewing, but all of the material, I don't think we're reviewing all of them. And I guess in the frame that you're probably thinking, I do think you're going to teach us, but I don't believe that we're reviewing everything that's in the lab, Alex, that we're being, that's given to us. So are we supposed to review with you during class and also follow up in a book to try to catch up on stuff on our own? Because it's a few questions in it and I'm like, we didn't go over this in class, so it's like confusing.
Well, like you said, you didn't start from the beginning of the class, so maybe you have missed something. But those questions in Alex, I choose them myself, and I made sure that I didn't go beyond what I taught in the class. So
that's what I was.
They might have a different formula for it, but like I said at the beginning of this class, in order not to get confused, use the formula I showed you here. Every question we covered I can't give you the same exact question that I taught. I have to give you a different question, but the concept is the same. Like I picked those questions myself. So it's not like somebody else picked them.
One thing that I know is that you did, but it came after we had it on the assignment. I can't remember what it's called, but it's a line chart. It was already on the assignment. You had showed us after the assignment was already due. And
no. That assignment, I created it. If you're talking about data description, let me show you the day I created that assignment, because everything is here. I think you're talking about if it is what homework is that? Homework 2 or 3?
I think it's in
2.
3.
3 homework 3 is
3 now. Is 3 now, or was it last?
Homework 3 is data description. So if you're talking about line graph, right?
No, it's not a line graph. I can't remember. Maybe it is a line graph.
Because homework 3, if it's this one, homework frequency distribution and graphs. Okay. Now I would if it's homework 2, then let me show you when I created homework 2. My announcement. See, this is week 1, homework 1. Okay, I make sure homework 1 is about. Let me go back again in the models. Homework 1 is introduction to statistics. So, but you're talking about line graphs, so you gotta be homework 2. Homework 2. So homework 2. This is week 3. Yep, this is when I created homework 2. And I created it, I posted this, what date? January 29th. January 29th, when I created this, made that post. So I created it and gave extra week, so that by the time it's come to the due date, we have covered everything. So 29th. So January 29th, is going back, is, see, January 29th, and it was due on February 11th. See, it's supposed to be due on, I didn't make it due on 4th. I make it due on 11th, 2 weeks. So that before it get to that point, we have already covered it. And each homework, I make it, you have unlimited attempts. So that if you don't cover it, if you do it and then you encounter something we haven't done before the due date, you can still do it again. So like I said, I picked everything myself and I give enough time for it. Okay. Any other question? All right, guys, I'll see you next week then. You have a good weekend.
Thank you,